So let's solve for the other half of question 3, part 3, where we want to find the slope dt dx for the head wave on a tx plot. So what I did here is I just went up and drew a diagram of what's going on in a head wave, right? A critically refracted wave, a head wave. We see here we have a source at point E. It is sending down a P wave at incident angle I. It reaches this interface here at point M. Then that wave is critically refracted. It's refracted straight along that interface between M and N. So the distance that it's refracted, the critical distance, is distance MN. And then after that distance, at point N, it is actually sent back up. It travels back up to the surface from N to G. And it reaches the surface at point G, where it's recorded and detected by a geophone, presumably, right? The velocity in this medium here is v1. The velocity in the lower medium is v2. We're assuming v2 is greater than v1 for these relations. That angle that it comes back up at between n and g is also equivalent to I, so they're the same angle. If you draw a 90-degree line from point M straight up, it is at point A, what we're calling point A, and the perpendicular to this interface at point N is point B. All these letters are going to be important when we're doing the geometric relationships to try to figure out what the time is going to be. And also notice this distance here, the distance between A and M, the distance between B and N vertically, that's the thickness of the layer, which is given H1, right? So the total travel, in order to find out what the slope is, we need to not, slope is distance over time, right? So we need to know both the distance, which is easy enough to solve for, right? The distance is going to be EM. When I say EM, I mean the length between E and M. So MN is the length between point M and point N. So the total distance that the wave travels is going to be EM plus MN plus NG, right? Simple enough. But slope isn't just distance, it's distance over time, right? So we need to figure out what the time components of each of those are for the total wave. In order to do that, we're going to find that it follows the following equation, which I'll write down here on the bottom. And when I'm done with that, you should be sure to copy this diagram and the equation, because these are going to be important to have later. I'm going to go ahead and erase them after this. So for total time for a head wave, it's going to be defined by time is equal to EM, right, that distance, divided by V1. And why EM over V1? Well, the time that it takes for the wave to go from this point to this point is not just that distance, but it's also distance, right? Time is defined by distance over velocity, right? If I want to know how long it's going to take me to go from my house to New York City, then I'm going to have to I have to know the distance, right? I have to know that it's so many miles away, but I also need to know how fast I'm going to be going, right? So it's going to be so many miles away, and I'm driving 60 miles per hour, and then I can calculate how long it's going to take me to get to New York City. The same thing happens with seismic waves, right? I want to know the time for this total path. I need to know the time for each component, and the time from E to M is going to be the distance EM divided by the velocity that I'll be traveling, or V1 in this case, plus this component, MN, divided by, in this case, it's traveling through velocity 2. A refracted wave, when it's traveling between two interfaces, travels at the velocity of the lower media, V2. And then the third component, we have this plus this, and we need to know the time that it takes to go this distance, which is going to be mg plus mg divided by, again, it's traveling through material v1 with velocity v1. Right, so there's our total travel time equation. It's a very simple form. We're going to fill in these variables next, but go ahead and copy down both this diagram and this equation, because you're going to need them later as reference. I'm going to go ahead and erase them now, so pause the video, copy them down, then we'll get to it. Right, good. Okay, so given that time equation that we just listed in the diagram we have there, we can see the diagram includes some triangles, right? So you can use your basic trig functions to solve for some of these values. If you know the lengths and you know the angles, right? We're given the angle, what was it? I believe it was 30 degrees. Yeah, I think it was 30 degrees that they initially gave us for I. So you're using I equals 30 degrees in this case. And we have angles, we have lengths. We can use trig functions with those triangles in the diagram to figure out what our values are going to be. Since we know using our trig functions that the cosine of that angle I is going to be equal to that length h1, remember on the side of the diagram h1 is the length, one of the lengths of that triangle, divided by the other length em. And we also know that em, in this case, is exactly equivalent to mg, and that em equals mg is equal to, em and mg are both equal to h1 divided by cosine I. Again, using our trig functions. And we can say that em equals mg equals h1 over cosine I, right? They're equivalent statements. Also, we know that EA equals BG equals h1 tangent I. Again, with our trig functions. And since the length mn is just going to be the total horizontal distance x minus EA plus BG, looking at your diagram, we can say that the total time travel equation is then going to simplify to this form. X minus 2 h1 divided by v2 plus h1 divided by v1 cosine I. Right? So that original time travel equation, em over v1 plus mn over v2 plus mg over v1, using our trig identities, we know all these equivalent statements, and you can use basic geometry to figure out that the lengths are equivalent in certain places, and you can use your SOHCAHTOA and your trigonometric relations to figure out that original time equation is equal to h1 divided by v1 over cosine I plus x minus 2h1 tangent I divided by v2 plus h1 divided by v1 cosine I. Those are equivalent equations. So right away, we've come away from a more generalized equation into something more specific that looks more useful. But we're going to go ahead and simplify this even further. So let's go ahead and call, we're going to erase this. Let's call this equation that we just finished here, we'll call it equation 2, right? We're going to go ahead and simplify equation 2 even further. We're going to make it more useful for our purposes here. I apologize if this is going off screen. I'm going to have to adjust this camera. Just a second here. Good enough. We can simplify equation 2 even further by saying equation 3 time equals 2h1 divided by v1 cosine I minus 2h1 times tangent of I divided by v2 plus x over v2. Right? That equation simplifies to form 3. And go ahead and erase equation 2. We're going to just go through a series of simplifications using substitutions of basic trig functions. So now we have this equation, this time equation in form 3. And we're going to modify equation 3 even further using these two relationships. So the first relationship we're going to modify it with is the fact that tangent of I is going to be equal to sine I minus sine I divided by cosine I, right? That's pretty simple. You should have learned that in trig class. Tangent theta equals sine theta over cosine theta, right? We're going to plug that into this equation. We're going to use that relationship, rather, to simplify the equation, along with this relationship, that sine I is going to equal v1 over v2, which stems from Snell's law, right? So we are going to modify equation 3 with these two relationships, and it yields what we're going to call equation 4. Actually, let me draw it out for you and then simplify it for, right? So we modify equation 3 with these two relationships, and that directly yields time equals 2h1 divided by v1 cosine I minus 2h1 sine squared I divided by v1 cosine I plus x over v2, right? So this equation modified with these two relations yields this equation, right? And we can simplify this equation even further to yield what we're going to call equation 4, another time travel equation, which is simply that time, the total travel time for a head wave is going to be equal to 2h1 times 1 minus sine squared. So 2h1 times 1 minus sine squared I divided by v1 cosine I plus x over v2. Right, so there's equation 4. This is the most useful equation we've come up with yet. So go ahead and copy down what you see on this board so you can reference it later, especially copy down equation 4, because I'm going to go ahead and erase this, and we're going to simplify this equation one more time into a new form. And then we can do fun stuff with it to turn it into dt dx, which is what we're all waiting for here. I know it's long and drawn out, but it needs to be done. So go ahead and copy this down, push pause if you need to. Go ahead and erase it. Probably have to realign this forward because I'm knocking it all over the place. Let's see if we can. Good enough. Right, so we just had equation 4. We can modify equation 4 using the relationships that we used before. Remember those two little trigonometric functions that I showed you? Those basic ones. We can use those two relationships from before and a third one, which is good old sine squared I plus cosine squared I. Sine squared I plus cosine squared I equals 1, right? Everybody should know that function. Don't do, you'll be happier, right? So we can use those two relationships from before plus this relationship, and we can substitute them into equation 4 to yield a new time equation for the head wave, which is going to be, from now on, I'm just going to write t instead of time. You'll understand that t means time, right? T equals the time total travel time for the head wave, t equals 2h1 cosine I divided by v1 plus x over v2. Or, we're going to expand it out a little bit. I know you're saying, well, why go from something simple to more complicated? Well, it's going to be prettier when we need to take the equation and we need to do the first derivative. So we're expanding it real quick. This little nice simple equation here is equivalent to 2h1 times 1 minus v1 squared divided by v2 squared, all raised, maybe I should put like more square brackets there, all raised to the 1/2 plus x over v2. Oh God, Alex, that looks awful. Why'd you do that? Well, it gets better. This equation here simplifies to 2h1 times v2 squared minus v1 squared raised to the 1/2 divided by v2 times v1 plus x divided by v2. Now, what we're going to call this is equation 5. This is the final simplification we need to do to this equation. Hooray. So go ahead and copy down equation 5. If you want to copy the rest, knock yourself out. But make sure you copy down equation 5 because I'm about to erase it again, and you're probably going to want to see how it works out. This is the final travel time equation for the head wave, but we need to turn it into a derivative, dx dt, right? Slope. That's not dx dt, that's just t. So go ahead, copy it down, pause the video if you need to. We're erasing. And equation 5 says that t equals 2h1 v2 squared minus v1 squared raised to the 1/2 divided by v2 times v1 plus x over v2. There's our equation 5 from before, but she wants us to give her the slope, dt dx. And so for this, we have to find the equation's first derivative. If you guys have done pre-cal, cal, you know how to do first derivatives. It's a very simple process. I won't go through it here, but I will say that it looks much nicer. So let's go ahead and just throw up what it equals, right? Finding the first derivative of this equation, t, yields dt dx equals something much, much nicer looking. That is it. dt dx, the slope of the head wave, is equal to 1 divided by the velocity of the lower rock medium. Isn't that nice and pretty? All done.